guys, welcome back to our channel. So, from today onwards, I'll be posting chemistry audiobooks for class 12. So, today we are dealing with Unit 4, the D and F block elements for class 12. So, I thought this chapter is a bit of theory based, so you might find it difficult to read it, the whole NCRT. So, I'll help you with it. So, just hear what I am reading and you'll understand it everything. So, let's start. Unit 4, the D and F block elements. Iron, copper, silver, and gold are among the transition elements that have played important roles in the development of human civilization. The inner transition elements such as thorium, palladium, and uranium are proving excellent sources of nuclear energy in modern times. The D block of the periodic table contains the elements of the groups 3 to 12 in which the D blocks are progressively filled in each of the 4 long periods. The F block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The names transition metals and inner transition metals are often used to refer to the elements of D and F block respectively. There are mainly 4 series of transition metals, that is D series, that is scandium to zinc, 4D series, that is yttrium to cadmium, 5D series, lanthanum and hafnium to mercury, and 6D series which has actinium and elements from rutherfordium to copernicium. The 2 series of the inner transition metals are 4F, that is cerium to lutetium, and 5F, thorium to lawrencium, are known as lanthanoid and actinoids respectively. Originally, the name transition metals was derived from the fact that their chemical properties were transitional between those of S and P block elements. Now, according to IUPAC, transition metals are defined as metals which have incomplete D subshell either in neutral atom or in their ions. Zinc, cadmium and mercury of group 12 have full D10 configuration in their ground state as well as their common oxidation states, and hence they are not regarded as transition metals. However, being the N members of the 3D, 4D and 5D transition series respectively, their chemistry is studied along with the chemistry of the transition metals. The presence of partly filled D or F orbitals in their atom makes transition elements different from that of the non-transition elements. Hence, transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to non-transition elements can be applied successfully to the transition elements also. Various precious metals such as silver, gold and platinum, and industrially important metals like iron, copper and titanium belonging to the transition metal series. In this unit, we shall first deal with the electronic configuration, occurrence and general characteristics of transition elements with spectral emphasis on the trends in the properties of the first row, that is 3D transition metals, along with the preparation and properties of some important compounds. This will be followed by consideration of certain general aspects such as electronic configurations, oxidation states, and chemical reactivity of the inner transition metals. 4.1 in position in the periodic table. The D block occupies the large middle section of the periodic table, flanked between S and the P blocks of the periodic table. The D orbitals of the penultimate energy level of atoms receive electrons, giving rise to 4 rows of the transition metals, that is 3D, 4D, 5D and 6D. All these transition series of elements are shown in table 4.1. 4.2 Electronic configurations of the D block elements. In general, the electronic configurations of outer orbitals of these elements is n-1d 1 to 10 ns 1 to 2, except for palladium where its electronic configuration is 4d10 5s0. The n-1 stands for the inner d orbitals, which may have 1 to 10 electrons, and the outermost ns orbitals may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference between n-1d and ns orbitals. Furthermore, half and completely filled set of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configuration of chromium and copper in the 3D series. For example, consider the case of chromium, which has 3d5 4s1 configuration instead of 3d4 4s2. The energy gap between the two sets, that is 3d and 4s of orbitals, is very small enough to prevent electron entering the 3d orbitals. Similarly, in case of copper, the configuration is 3d10 4s1 and not 3d9 4s2. The ground state of electronic configurations of the outer orbitals of transition elements are given in table 4.1. The electronic configurations of outer orbitals of zinc, cadmium, mercury and copernicium are represented by the general formula n-1 d10 ns2. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. The d orbitals of the transition elements protrude to the periphery of an atom more than the other orbitals, that is S and P. Hence, they are more influenced by the surroundings as well as affect the atoms or molecules surrounding them. In some respects, ions of the given Dn configuration, that is n is equals to 1 to 9, have similar magnetic and electronic properties. With partly filled d orbitals, these elements exhibit certain characteristic properties such as display of variety of oxidation states, formation of colored ions, and entering into complex formation with a variety of ligands. The transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater similarities in the properties of transition elements of a horizontal row in contrast to the non-transition elements. However, some group similarities also exist. We shall first study the general characteristic and their trends in the horizontal rows, particularly the 3D row, and then consider some group similarities. We will discuss the properties of the elements of first transition series only in the following sections. 4.3 General properties of the transition elements, that is D block. 4.3.1 Physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. With the exceptions of zinc, cadmium, mercury, and manganese, they have one or more typical metallic structures at normal temperatures. The transition metals, with the exception of zinc, cadmium, and mercury, are very hard and have low volatility. Their melting and boiling points are very high. Figure 4.1 depicts the melting point of transition metals belonging to 3D, 4D, and 5D series. The high melting point of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to the ns electrons in the interatomic metallic bonding. In any row, the melting points of these metals rise to maximum at D5 except for anomalous values of manganese and technetium and fall regularly as the atomic number increases. They have high enthalpies of atomization, which are shown in the figure 4.2. The maxima at about the middle of the series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resulting bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, metals with very high enthalpy of atomization, that is very high boiling point, tends to be noble in their reactions. See later for electrode potentials. Another generalization that may be drawn from figure 4.2 is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal-metal bonding in compounds of the heavy transition metals. 4.3.2 Variation in atomic size and atomic and ionic size of transition metals. In general, ions of the same charge in a given series show progressive decrease in radius with increase in atomic number. This is because new electron enters a d orbital each time the nuclear charge decreases by unity. It may be recalled that the shielding effect of a d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. The same trend is observed in the atomic radii of a given series. However, the variation within a series is quite small. An interesting point emerges when atomic sizes of one series are compared to those of corresponding elements in the other series. The curve in figure 4.3 shows an increase from the first, that is 3D, to the second, that is 4D series of the elements, but the radii of the third, that is 5D series, are virtually the same as of the corresponding members of the second series. This phenomenon is associated with the intervention of 4f orbital which must be filled before the 5D series of elements begin. The filling of 4f before 5D orbital results in a regular decrease in atomic radii called lanthanoid contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. The net result of the lanthanoid contraction is that the second and the third D series exhibits similar radii. Example: zirconium 160 picometer, hafnium 159 picometer, and have very similar physical and chemical properties, much more than that expected on the basis of usual family relationship. The factor responsible for the lanthanoid contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar cause, that is imperfect shielding of one electron by another in the same set of orbitals. However, the shielding of one 4f electron by another is less than that of 1d electron by another, and as the nuclear charge increases along the series, there is fairly regular decrease in the size of entire 4fn orbitals. The decrease in metallic radius coupled with increase in atomic mass results in a general increase in the density of these elements. Thus, from titanium, that is Z is equals to 22, to copper, that is Z is equal to 29, the significant increase in the density may be noted in table 4.2. 4.3.3 Ionization enthalpies. There is an increase in ionization enthalpy along each series of the transition elements from the left to the right due to an increase in nuclear charge which accompanies the filling of inner d orbitals. Table 4.2 gives the values of the first three ionization enthalpies of first series of transition elements. These values show that the successive enthalpies of these elements do not increase as steeply as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to variation along a period of non-transition elements. The first ionization enthalpy in general increases, but the magnitude of increase in the second and the third ionization enthalpies for successive elements is much higher along a series. The irregular trend in the first ionization enthalpy of the metals of 3D series, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3D orbitals. You have learned that when d block elements form ions, ns electrons are lost before n-1 d electrons. As we move along the period in 3D series, we see that nuclear charge increases from the scandium to zinc, but electrons are added to the orbital of inner subshell, that is 3D orbital. These 3D electrons shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. Therefore, the atomic radii decreases less rapidly. Thus, ionization energies increase only slightly along the 3D series. The doubly or more highly charged ions have DN configuration with no 4s electrons. A general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increase, because one d electron does not shield another electron from the influence of nuclear charge, because d orbitals differ in direction. However, the trend of steady increase in the second and the third ionization enthalpy breaks for formation of Mn2+ and Fe3+ respectively. In both the cases, ions have d5 configuration. Similar breaks occur in corresponding elements in the later transition series. The interpretation of variation in ionization enthalpy for an electronic configuration Dn is as follows. The three terms responsible for the value of ionization enthalpy are attraction of each electron towards the nucleus, 2. repulsion between the electrons, and 3. the exchange inner energy. The exchange energy is responsible for the stabilization of energy state. Exchange energy is approximately proportional to the total number of possible pair of parallel spins in the degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins. That is Hund's rule. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy at D6 configuration. Mn plus and 3d5-4s1 configuration and configuration of chromium plus is 3d5. Therefore, ionization enthalpy of manganese plus is lower than chromium plus. In the same way, Fe2+, that is iron 2+, has D6 configuration and manganese 2+ has 3d5 configuration. Hence, ionization enthalpy of Fe2+ is lower than manganese 2+. In other words, we can say that the third ionization enthalpy of Fe is lower than that of Mn. The lowest common oxidation state of these metals is +2. To form the M2+ ions from the gaseous atom, the sum of the first and second ionization enthalpy is required in addition to the enthalpy of atomization. The dominant terms is the second ionization enthalpy, which shows unusually high values for chromium and copper, where M+ ions have the 3d5 and 3d10 configurations respectively. The value of zinc is correspondingly low, as the ionization causes the removal of one 4s electron, which results in the formation of stable D10 configuration. The trend in the third ionization enthalpy is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from the D5, that is Mn2 plus, and D10, that is zinc 2 plus ions. In general, the third ionization enthalpies are quite high. Also, the high values for the third ionization enthalpies of copper, nickel, and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpies give some guidance concerning the relative stabilities of oxidation states, this problem is very complex and not amenable to ready generalization. One of the notable features of a transition elements is the great variety of oxidation states these may show in their compounds. Table 4.3 lists the common oxidation states of the first row transition elements. The elements which give the greatest number of oxidation states occur in or near the middle of the series. Manganese, for example, exhibits all the oxidation states from +2 to +7. The lesser number of oxidation states at the extreme ends stems from either too few electrons to lose or share, that is scandium and titanium, or too many d electrons, hence fewer orbitals available in which to share electrons with others for higher valence, that is copper and zinc. Thus, early in the series, scandium 2 is virtually unknown and titanium 4 is more stable than titanium 3 or titanium 2. At the other end, the only oxidation state of zinc is +2 and no d electrons are involved in it. The maximum oxidation state of reasonable stability corresponds in the value to the sum of the S and D electrons up to manganese. Ti4O2, V5O2 plus, Cr4O42O42 minus, Mn7O4, followed by a rather abrupt decrease in stability of higher oxidation states, so that the typical species to follow are Fe2,3, cobalt 2,3, nickel 2, copper 1,2, and zinc 2. The variability of oxidation states, a characteristic of transition elements, arise out of incomplete filling of d orbital in such a way that their oxidation states differ from each other by unity. Example: vanadium 2, vanadium 3, vanadium 4, and vanadium 5. This is in contrast with the variability of oxidation states of non-transition elements, where oxidation states normally differ by a unit of 2. An interesting feature in the variability of oxidation states of the D block elements is noticed among the group 4 through 10. Although in the P block the lower oxidation states are favored by the heavier members due to inert pair effect, the opposite is true in the groups of D block. For example, in group 6, molybdenum 6 and tungsten 6 are found to be more stable than chromium 6. Thus, chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas molybdenum, that is MoO3, and tungsten, that is WO3, are not. Low oxidation states are found when a complex compound has ligands capable of pi acceptor character in addition to the sigma bond A. For example, in NiCO4 times and FeCO5 times, the oxidation state of nickel and iron is 0. Table 4.4 contains, the heading is 4.3.5, trends in M2 plus bar M standard electrode potential. Table 4.4 contains the thermochemical parameters related to the transformation of the solid metal atoms to M2 plus ions in solution and their standard electrode potentials. The observed values of E minus and those calculated using the data of table 4.4 are compared in figure 4.4. The unique behavior of copper having a positive electrode potential accounts for its inability to liberate hydrogen from acids. Only oxidizing acids, that is nitric acid, and hot concentrated sulfuric acid react with copper, the acids being reduced. The high energy to transform copper, that is solid, to Cu2 plus aqueous is not balanced by this hydration enthalpy. The general trend towards less negative electrode potential values across the series is related to general increase in the sum of first and second ionization enthalpies. It is interesting to note that the value of electrode potential for manganese, nickel and zinc are more negative than compared to the trend. The stability of the half-filled D subshell in Mn2 plus and the completely filled D10 configuration of Zn2 plus are related to their E0 values, whereas E0 for Ni is related to the highest negative hydration enthalpy. 4.3.6 Trends in M3 plus bar M2 plus standard electrode potentials. An examination of the electrode potential of M3 plus bar M2 plus values, that is from table 4.2, shows the varying trends. In low value for scandium reflects the stability of scandium 3 plus, which has a noble gas configuration. The highest value of zinc is due to the removal of an electron from the stable D10 configuration of Zn2 plus. The comparatively high value of manganese shows that Mn2 plus, that is D5 configuration, is particularly stable, whereas comparatively low value for iron shows the extra stability of Fe3 plus, that is D5. The comparatively low value for vanadium is related to stability of V2 plus, that is half-filled T2G level. This is from Unit 5. 4.3.7 Trends in stability of higher oxidation states. Table 4.5 shows the stable halides of the 3D series of transition metals. Highest oxidation numbers are achieved in TiX4, that is tetrahalides, and VF5 and CrF6. Those are examples. The plus 7 state for Mn is not represented in simple halides, but MnO3F is known, and beyond Mn no metal has trihalide except FeX3 and COF3. The ability of fluorine to stabilize the highest oxidation state is due to their higher lattice energy, as in the case of cobalt fluoride, that is COF3, or higher bond enthalpy terms of the higher covalent compounds, example VF5 and CrF6. Although vanadium plus 5 is represented only by VF5, the other halides, however, undergo hydrolysis to give oxohalides, that is VOX3. Another feature of fluorohalides is their instability in the low oxidation states, that is VX2, X is equal to Cl, Br or I. And the same applies to CuX, that is copper halide. On the other hand, all Cu2 plus halides are known except the iodide. In this case, Cu2 plus oxidizes I minus to I2. The reaction is as follows: 2Cu plus plus 4I gives Cu2 I2, that is solid state, plus I2. However, many copper 1 compounds are unstable in the aqueous solution and undergo disproportionation. The reaction 2Cu plus gives Cu2 plus plus Cu. The stability of Cu2 plus aqueous rather than Cu plus aqueous is due to the much more negative hydration enthalpy of Cu2 plus aqueous than Cu plus. Which more than compensates for the second ionization enthalpies of Cu. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation number in the oxides coincide with a group number and is attained in SCO3 to Mn2O7. Beyond group 7, no higher oxides of Fe above Fe2O3 are known, although ferrates that is 6 oxidation number FeO4 minus are formed in alkaline media, but they readily decompose to Fe2O3 and O2. Besides the oxides, oxocations stabilize V5 as VO2 plus, V4 as VO2 plus, and Ti4 as TiO2 plus. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. Thus, the highest manganese fluoride is MnF4, whereas the highest oxide is Mn2O7. The ability of oxygen to form multiple bonds to metals explains its superiority. In the covalent oxide Mn2O7, each Mn is tetrahedrally surrounded by O's, including MnO Mn bridge. The tetrahedral MnO4N- ions are known for vanadium 5, chromium 6, manganese 5, manganese 6, and manganese 7 as well. 4.3.8 Chemical reactivity and electrode potential values. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble, that is, they are unaffected by single acids. The metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1 molar H+, though the actual rate of which these metals react with oxidizing agents like hydrogen ion, that is H+, is sometimes slow. For example, titanium and vanadium in practice are passive to dilute non-oxidizing acids at room temperature. The E0 values for Mn2 plus bar M in table 4.2 you saw that indicate the decreasing tendency to form divalent cations across the series. This general trend towards less negative electrode potential values is related to the increase in the sum of the first and the second ionization enthalpies. It is interesting to note that E0 values for Mn, Ni, and Zn are more negative than expected from the general trend, whereas the stabilities of half-filled D subshell D5 in Mn2 plus and completely filled D subshell D10 in zinc are related to their E0 values. For nickel, E0 value is related to the highest negative enthalpy of hydration. An examination of E0 values for the redox couple M3 plus bar M2 plus from table 2.2 only shows that Mn3 plus and CO3 plus ions are the strongest oxidizing agents in aqueous solution. The ions titanium 2 plus and vanadium 2 plus and chromium 2 plus are strong reducing agents and will liberate hydrogen from a dilute acid. Example, 2Cr2 plus aqueous plus 2 hydrogen plus aqueous gives 2 chromium 3 plus aqueous plus hydrogen gas. 4.3.9 Magnetic properties. When a magnetic field is applied to a substance, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Diamagnetic substances are repelled by an applied field, while the paramagnetic substances are attracted. Substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Paramagnetism arises from the presence of unpaired electrons, each such electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compounds of the first series of transition metals, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. For these, the magnetic moment is determined by the number of unpaired electrons and is calculated by using spin only formula, that is mu is equals to root of n into n plus 2, where n is the number of unpaired electrons and mu is the magnetic moment in units of Bohr magneton or Bm. A single unpaired electron has a magnetic moment of 1.73 Bohr magneton. The magnetic moment increases with the increase in number of unpaired electrons. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electrons present in the atom. molecule or ion. The magnetic moments calculated from the spin-only formula and those derived experimentally for some ions of the first row transition elements are given in table 4.7. The experimental data are mainly for hydrated ions in solution or in the solid state. 4.3.10 Formation of colored ions. When an electron from a lower energy d orbital is excited to a higher energy d orbital, energy of excitation corresponds to its frequency of light absorbed. This frequency generally lies in the visible region. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of the ligand. In aqueous solutions where water molecules are the ligands, the color of the ions observed are listed in table 4.8. A few colored solutions of the D block elements are illustrated in figure 4.5. So, in figure 4.5, colors of some of the first row transition metal ions in aqueous solution are given. From left to right, we have vanadium 4 plus, vanadium 3 plus, manganese 2 plus, Fe3 plus, CO2 plus, nickel 2 plus, and copper 2 plus. So, 4.3.11 Formation of complex compounds. Complex compounds are those in which the metal ions bind a number of anions or neutral molecules, giving complex species with characteristics properties. A few examples are FeCN6 times 3 minus, FeCN6 4 minus, CuNH3 4 2 plus, and BtCl4 2 minus. The chemistry of complex compound is dealt with in detail in Unit 5. The transition metals form a large number of complex compounds. This is due to the comparatively smaller sizes of metal ions, the high ionic charges, and the availability of d orbitals for bond formation. The transition metals and their compounds are known for their catalytic activity. This activity is ascribed to their ability to adopt multiple oxidation states and form complexes. Vanadium oxide in contact process, finely divided iron in Haber's process, and nickel in catalytic hydrogenation involve the formation of bonds between reactant molecules and atom of the surface of the catalyst. First row transition metal utilize 3d and 4s electrons for bonding. This has the effect of increasing the concentration of the reactant at the catalyst surface and also weakening of the bonds in the reacting molecules. The activation energy is lowering. Also, because transition metal ions can change their oxidation states, they become more effective as catalysts. For example, iron 3 catalyzes the reaction between iodide and persulfate ions. That is 2I minus plus S2O8 2 minus gives I2 plus 2 SO4 2 minus. Here S2O8 2 minus means persulfate. An explanation of this catalytic action can be given as 2 Fe3 plus 2 I minus gives 2 Fe2 plus I2, or in other words 2 Fe2 plus S2O8 2 minus gives 2 Fe3 plus 2 SO4 2 minus. 4.3.13 Formation of interstitial compounds. Interstitial compounds are those which are formed when small atoms like H, C, or N are trapped inside the crystal lattices of metals. They are usually non-stoichiometric and are neither typically ionic nor covalent. For example, TiC, Mn4n, Fe3H, VH 0.56 and TiH 1.7, etc. Formulas quoted do not of course correspond to any normal oxidation state of the metal because of the nature of their composition. These compounds are referred to as interstitial compounds. The principal physical and chemical characteristics of these compounds are as follows. 1. They have high melting points, higher than those of pure metals. They are very hard. Some borides approach diamond in hardness. They retain metallic conductivity. They are chemically inert. 4.3.14 Alloy formation. An alloy is a blend of metals prepared by mixing components. Alloys may be homogeneous solid solution in which the atoms of one metal are distributed randomly among the atoms of the other. Such alloys are formed by the atoms with metallic radii that are within about 15% of each other. Because of similar radii and other characteristics of transition metals, alloys are readily formed by these metals. The alloys so formed are hard and have often high melting points. The best known are ferrous alloys. Chromium, vanadium, tungsten, molybdenum, and manganese are used for the production of a variety of steels and stainless steel. Alloys of transition metals with non-transition metals such as brass, there is copper and zinc, and bronze, copper and tin are also considerable industrial importance. 4.4 Some important compounds of transition elements. 4.4.1 Oxides and oxoanions of metals. These oxides are generally formed by the reaction of metals with oxygen at high temperatures. All the metals except scandium form MO oxides, which are ionic. The highest oxidation number in the oxides coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Besides the oxide, the oxocation stabilizes vanadium 5 as V2O plus and V4 as VO2 plus and titanium 4 as TiO2 plus. As the oxidation number of a metal increases, ionic character decreases. In the case of manganese, Mn2O7 is a covalent green oil. Even CrO3 and V2O5 have low melting points. In these higher oxides, acid character is predominant. Thus, Mn2O7 gives MnO4 and CrO3 gives H2CrO4 and H2Cr2O7. V2O5 is however amphoteric, though mainly acidic, and it gives VO4 3 minus as well as VO2 plus salts. In vanadium, there is a gradual change from the basic V2O3 to less basic V2O4 and amphoteric V2O5 to V2O4 dissolves in acids to give VO2 plus salts. Similarly, V2O5 reacts with alkalis as well as acids to give VO4 3 minus and VO4 plus respectively. The well characterized CrO is basic but CrO3 is amphoteric. Again, CrO is basic but Cr2O3 is amphoteric. Potassium dichromate K2Cr2O7. Potassium dichromate is a very important chemically used in leather industry and as an oxidant for preparation of many azo compounds. Dichromates are generally prepared from chromate, which in turn are obtained by the fusion of chromite ore with sodium or potassium carbonate in free access of air. The reaction with the sodium carbonate occurs as follows. 4 FeCr2O4, that is chromite ore, plus 8 Na2CO3, that is sodium carbonate, plus 7 O2 in the presence of air supply gives 8 Na2CrO4, that is sodium chromate, which is yellow color, plus 2 Fe2O3 and 8 CO2. The yellow solution of sodium chromate is filtered and acidified with the sulfuric acid to give a solution from which orange sodium dichromate Na2Cr2O7 dot 2H2 can be crystallized. 2 Na2CrO4 plus 2H plus gives Na2Cr2O7 plus 2Na plus H2O, where Na2Cr2O7 sodium dichromate is orange in color. Sodium dichromate is more stable than potassium dichromate. The latter is therefore prepared by treating the solution of sodium dichromate with the potassium chloride. Na2Cr2O7 plus 2KCl gives K2Cr2O7 plus 2NaCl. Orange crystals of potassium dichromate crystallize out. The chromates and dichromates are interconvertible in aqueous solution depending upon the pH of the solution. The oxidation state of chromium in chromate and dichromate is the same. 2CrO4 2 minus, that is chromate, plus 2H plus acid gives Cr2O7 2 minus plus H2O. Next, Cr2O7 2 minus dichromate plus O2OH minus, that is in basic medium, has 2 CrO4 2 minus plus H2O. These are the interconventions. The structures of chromate ion, that is CrO4 2 minus, and the dichromate ion, that is Cr2O7 2 minus, are shown below. The chromate ions is tetrahedral, whereas the dichromate ion consists of two tetrahedral sharing one corner with a CrO-Cr bond angle of 126 degree. Sodium and potassium dichromates are strong oxidizing agents. The sodium salt has greater solubility in water and is extensively used as oxidizing agent in organic chemistry. Potassium dichromate is used as primary standard in volumetric analysis. In acidic solution, its oxidizing action can be represented as Cr2O7 2 minus plus 14H plus 6 electrons give 2 Cr3 plus 7 H2O with an electrode potential of plus 1.33 volt. Thus, acidified potassium chromate will oxidize iodides to iodine, sulfides to sulfur, tin 2 to tin 4, and iron 2 to salt to iron 3. The half reactions are noted below. That is 6I minus gives you 3I2 plus 6 electron, 3H2S gives you 6H plus 3S plus 6 electron, and 3SN2 plus gives 3SN4 plus 6 electron, and 6Fe2 plus gives 6Fe3 plus 6 electron. The full ionic equation may be obtained by adding the half reaction for potassium dichromate to the half reaction of the reducing agent. For example, we have Cr2O7 2 minus plus 14H plus 6 Fe2 plus gives 2 Cr3 plus 3 Fe3 plus 7 H2O. So you have to actually look into your NCERT book, then only it will be clear. So just go through it once. Potassium permanganate KMnO4. Potassium permanganate KMnO4 is prepared by the fusion of MnO2 with alkali metal hydroxide and an oxidizing agent like KNO3. This produces the dark green K2MnO4, which disproportionates in a neutral or acidic solution to give permanganate. 2MnO2 plus 4KOH plus O2 gives 2K2MnO4 plus 2H2O. 3MnO4 2 minus plus 4H plus gives 2MnO4 minus plus MnO2 plus 2H2O, where MnO4 minus is called as permanganate. Commercially, it is prepared by the alkaline oxidative fusion of MnO2 followed by the electrolytic oxidation of manganate 6. So let me summarize this. MnO2 fused with KOH oxidized with air or KNO3 is converted to MnO4 2 minus, which is manganate ion. Also, MnO4 2 minus manganate on electrolytic oxidation in alkaline solution gives you MnO4 minus or permanganate ion. In the laboratory, a manganese 2 ion salt is oxidized by peroxy disulfide to permanganate. 2Mn2 plus 5S2O A2 minus plus 8H2O gives 2MnO4 minus plus 10SO4 2 minus plus 16H plus. Again, I am telling you will have to just take your NCERT out and just read the reactions by yourself. Potassium permanganate form dark purple, almost black crystals which are isostructural with those of KClO4. The salt is not very soluble in water, but when heated it decomposes at 513 Kelvin. There is an important equation, that is 2 KMnO4 when heated gives you K2MnO4 plus MnO2 plus O2. It has two physical properties of considerable interest: its intense color and its diamagnetism, along with the temperature dependent weak paramagnetism. These can be explained by the use of molecular orbital theory, which is beyond the present scope. The manganate and permanganate ions are tetrahedral. The pi bonding takes place by overlap of the p orbitals of oxygen with the d orbitals of manganese. The green manganate is paramagnetic because of the unpaired electron by the Permanganate is diamanganate due to the absence of unpaired electron. Acidified permanganate solution oxidizes oxalate to carbon dioxide, iron 2 to iron 3, nitrite to nitrate, and iodides to free iodine. The half reactions of reductants are given below. The full reaction can be written by adding the half reaction for KMnO4 to the half reaction of the reducing agent, balancing wherever necessary. If we represent the reduction of permanganate to manganate, manganese dioxide and manganese 2 salt by half reactions, we get a couple of formulas, that is MnO4 minus plus electron gives you MnO4 2 minus, MnO4 minus plus 4H plus gives you MnO2 plus 2H2O, MnO4 minus plus 8H plus 5 electron gives you Mn2 plus 4 water. We can very well see that hydrogen ion concentration of the solution plays an important part in influencing the reaction. Although many reactions can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. Permanganate at H plus is equal to 1 should oxidize water, but in practice the reaction is extremely slow unless either manganese ions are present or temperature is raised. A few important oxidizing reactions of KMnO4 are given below. First one, in acidic solution, iodine is liberated from potassium iodide. Second one is Fe2 plus ion, that is green, is converted into Fe3 plus, that is yellow. And then we have third one, oxalate ion or oxalic acid is oxidized as 333 Kelvin. Hydrogen sulfide is oxidized, sulfur being precipitated. Then fifth one, sulfurous acid or sulfite is oxidized to sulfate or sulfuric acid. Then sixth one is nitrite is oxidized to nitrate in neutral or faintly alkaline solutions. A notable reaction is the oxidation of iodide to iodate. Then we have thiosulfate is oxidized to quantitatively to sulfate. Then manganese salt is oxidized to MnO2. In the presence of zinc sulfate or zinc oxide catalyzes the oxidation. So that you have to keep in mind. So that's all for D block. Then inner transition elements will be covered in another video. Till then, take care and bye bye. So please comment down below if you need the next part of the inner transition elements F block. Thank you.